For today's lesson, our focus standard comes from Grade 7, Statistics and Probability, Standard 3. Informally assess the degree of visual overlap of two numerical data distributions. Our topic comes from Data and Statistics, Compare Measures of Variability. Our essential question is, what do we look for when comparing two or more dot plots or box and whisker plots in our data analysis? Please take a moment, pausing the video if you need to copy down the topic and essential question into your header, along with today's date, set up your question column and your note column, and resume the video when you're ready to begin. Let's begin with a review of what we mean by measures of variability. We're talking about mean, median, mode, and range. We've been working a lot with mean, which is calculating the average of the data set. What do you remember about median, mode, and range? Well, median, like MED for medium-sized cup, finds the middle of the data set. Mode identifies the data point that shows up the most. And range calculates the spread of the data set by subtracting the lowest value from the highest value. Between mean, median, and mode, it's important to know when to use which of these calculations. Sometimes we calculate all three, but in real life, it usually depends on the situation and the data set that we're examining. The mean is best used with symmetrical data sets. Median is best used with asymmetrical data sets. And mode is best used when wanting to know what's most popular among the data. So, with this review in mind, we're going to start first by comparing some data that is shown to us in a dot plot. Let's go ahead and take a look. Here I've created and shown the dot plots that are showing test scores from two different classes. And then I've asked some questions about comparing them. Which class had the higher mean test score? Which class had the higher range of test scores? In total, how many students did not pass the test, meaning they scored below 70? Well, take a look at this data and start to predict some of the answers, or start to think about how you might answer those questions. One thing I notice about the first question, asking us to collect the mean, is on a dot plot, we don't know precisely what these numbers are, all of them. Some of them we can see right away. This looks like the student scored exactly 100 out of 100 on that test. And these two students are pretty close to 70, but what if that's 71? And is this 72 or 73? So we have a pretty good idea, but we don't know the exact values. So if we don't know the exact values, we can't add up all the scores and divide by the number of students. So what do you see in the data that allows us to predict or answer this question, perhaps without having to calculate it? If you said we can take a look at the shape of the data, I'd agree with you. Our data is pretty symmetrical, which is one of the things we wanted to look for when using mean. There are some lower scores here, but there's also some high scores here that balance that out. It kind of has this general bell shape. What would make it asymmetrical is if we had this shape, but we also had some numbers like way down here with large gaps. That would mean that it's not symmetrical. But our data sets here are symmetrical, and so we can begin to predict where we think the mean of this data set would be. So where do you think the average of these points here for Class A would be? I myself would put it somewhere in the range of right around here. Because that looks like, well, it's also where it rises, but it also looks like about the average score. Some of these scores cancel out. But it looks like most students, the average was right around 83 or 84 out of 100. What do you think about for Class B? But then it looks a little bit lower. I might put it here at 75. perhaps a little bit lower, but it's hard to say, but it would be here. Would definitely be lower than Class A. So even without being able to calculate it, the shape of our dot plots, and we can kind of infer about where the mean would be for each class. So for this first question, which class had the higher mean test score? I would say Class A, and I could even infer that it's about 8 points higher. Which class had the higher range of test scores? Well, remember, range is the calculation of the spread. So, which has a more spread out data set? Well, for that question, I would say Class B. And I'm looking at the highest score, which is about 95, and the lowest score, which is 55. If I subtract those, I see it has a spread on the number line of 40 points. So lastly, as we compare these two data distributions of their test scores, in total, how many students did not pass the test below 70? So in total, between the two classes, how many students did not pass? Well, if we look at each one, find 70 and count the ones below it, I've highlighted those in orange. And it looks to me between the two classes, there are 6 students who did not pass the test. So I hope that this is giving us an indicator that these calculations, these means of measurability, are very helpful. And sometimes, though, with our data, we can't always do exact calculations, like we couldn't do our exact calculation of our mean. However, by looking at the shape of the data, we can predict or infer about where the mean will be. And that oftentimes is enough to be able to compare the two data sets. Let's go ahead and look at some box and whisker plots. While I was looking online, I found a reference that showed me the price of homes for sale in Chicago and Los Angeles over a 2-week time period in 2013. Take a little bit of time just looking at these two box plots and the information that we're given about the price of the homes, and what do you just notice in general? So let's take a closer look at these problems and see if we can come up with some more precise answers. Our first question is, which city has a higher median price of homes for sale? Well, you might remember from 6th grade that in order to make these box and whisker plots, you have to order your data from least to greatest, so we can actually see a lot of those points here for both cities. And you calculate the median, calculating which number is in the middle. And then we mark that with the line that becomes the middle, or the line within our box, on our box and whiskers. So here are 2 medians for price homes in LA and Chicago. And it looks like it fits the trend of what we noticed at the generalizations we noticed at the beginning. LA has a higher median price. It's almost $500,000. And it looks to me like Chicago's almost half of that. Like I would estimate that to be about $250,000. So for our first question, I would say that Los Angeles has a higher median price of homes. That was pretty clear. And it's almost 2 times as high. Which city has a higher range of home prices? Well, once again, range is calculating from the lowest point to the highest point. In this case, though, why are these points not included in this whisker? The whisker for this top part of the data, the top 25%, stops right here at just over $1 million. Whereas with Chicago, that whisker, that top whisker stops just about maybe 700,000. Why are these points not included? Well, you might remember that points that are considered outliers are not included in the whiskers. And so for the range, I would just keep in mind the range between the bottom whisker and the top whisker. But once again, it looks like LA has a longer range in values. The lowest value is maybe 1,000, hard to tell here, maybe under 1,000. but Chicago's right at 0. Chicago only reaches up to about 700,000, where LA goes beyond $1 million. So I would say that the city with the higher range of home prices would be LA. And in fact, that range is a little more than $1 million difference between the lowest price and the highest price. One thing I want to point out here that makes box and whisker plots a better choice to use than maybe a dot plot here is that home prices range a lot, and I hope you can see that there's quite a few outliers, especially this house way up here at like 4,250,000, right? That's really high, and that's a huge gap. So this would be a really good example of asymmetrical data. It's not all clustered together in a condensed range. It has a really spread out range, and these are definitely considered outliers. Even for Chicago, most of the data is right around in here, but there's some outliers that kind of skew our data. So had we calculated average rather than median, it would look like the price of homes in both cities were a lot higher than they actually are because of the outlier prices. So oftentimes with prices of things, we get asymmetrical data sets, and that's why we use the median calculations in a box and whisker rather than calculating the mean. Our third question says, which city has a higher interquartile range? Well, interquartile is the middle 50% of the data, so that's this range of the box that makes up our box and whisker plots. And once again, we see that the width of this box, or the height of this box in this case, since it's aligned vertically for Chicago, is definitely shorter than the box, which is representing the middle 50% of the data for LA. So once again, LA has a higher range in interquartile range of price. Lastly, our question asks, how many homes in total in the two cities cost more than $1.5 million? So that's to draw our attention to that we're actually given all the data points here and we can see them. And so each point here represents a home for sale in one of these two cities. How many do you see between the two homes that are listed at more than $1,500,000? Well, I counted them up. Hopefully you agree. I would say that there are 9 homes between the two cities in this 2-week time period in 2013 that were for sale for more than $1,500,000 or $1.5 million.